Good morning students. This is lecture 15 under module 5. As you know, I told you I think in the last class that till now we have discussed the basics of membrane, what is the membrane, what are its advantages, disadvantages, how transport takes place inside the membrane. Then we have also discussed the different materials that is used for preparing membrane, whether it is polymeric or whether it is ceramic. Their properties, their advantages, disadvantages, all these things. Then we have proceeded and we have discussed how to prepare a membrane. So, by different techniques. So, we have discussed this one, how to prepare porous membrane, and then we have also discussed how to prepare composite membranes by various techniques. Then we went and discussed the transport in membranes. After that we have started phase by phase. We are going to start basically the different membrane processes and detailed discussion about their things, and I just forgot to mention that we have also discussed about membrane modules in detail. So, I have decided that it is better, we have already covered 14 lectures, almost half of the this one scheduled lectures. So, let us just revise what we have discussed today. So, today's lecture is dedicated for the revision of concepts and fundamentals till we have till that we have whatever we have covered. So, let us begin. So, quickly we will see different concepts basically. As we understand, membrane is of course a semi permeable perm selective barrier, and it is an interface between two phases that allows passage of certain things go through, whereas it stops others. So, now that these things may be, they may be molecule, they may be ions, may be smaller particles, and there is a driving force that does the separation in case of membranes, and driving force can be of many types. It can be either concentration difference, it can be temperature difference, it can be pressure difference, or it can be electromotive force difference. So, usually the phase 1 is the feed phase, which also we call is at the upstream side, and phase 2 is the downstream side or the permeate side. So, this is just a schematic of the usual membrane process. So, the performance of given membrane is determined by following two parameters: selectivity and flow through. So, you know the term flow through means it is nothing but the flux or the permeation rate. So, it can be denoted as the volume flowing through the membrane per unit area and unit time. So, the selectivity of the membrane can be defined by two ways. One is retention, that is R, or rejection, and another is separation factor alpha. So, retention is much more important respect to membrane. So, retention or rejection can be defined as Cf minus Cp by Cf or 1 minus Cp by Cf. So, Cf is the solute concentration in the feed, Cp is the solute concentration in the permeate. R is a dimensionless parameter, it does not depend on the units in which the concentration is expressed. The value of R varies from 100%, means that is complete retention of the solute, to 0%. Solute or solvent pass through the membrane freely, there is no retention. There are many benefits or advantages of membrane separation. The first and foremost important is of course the energy consumption is low. Then membrane processes can be easily combined with separation processes. This is called hybrid processes basically. So, in our subsequent discussions we will discuss how membrane has been clubbed with distillation process to make hybrid processes. As you know, the upscaling is also easy. Membrane properties are variable and can be adjusted. So, in many classes I have already told that membrane, a particular membrane can be tailor made. Just like a tailor stitches our suit or this one shirt or pant, whatever it is, similar way we can make a membrane which is selectively applicable for a particular target pollutant. You can say pollutant or molecule or solute, whatever it is. So, let us say I am targeting the separation of a particular pollutant. I am just giving an example of wastewater treatment which is present along with other pollutants, but I am targeting that one because that is more toxic. Okay, others can be removed by other techniques, right? And concentration also depend whether concentration is high or concentration is low. So, I can make a membrane which will selectively either retain this particular pollutant or it can be permeated through the downstream side. So, this is what is the meaning of tailor make actually, and you do not need any additives in membrane separation, just like you add we need extractant, in LLE, or we need another solvent to break azeotropes in case of distillation columns. But nevertheless, there are certain drawbacks. The first important drawback is of course the concentration, polarization and membrane fouling. So, I am not going to discuss again on all these things. Today's lecture is devoted to that, just brief discussion about and revising the concepts, and we know what is concentration, polarization. Just again I am just telling you, let us say this is the membrane. So, the solutes are getting deposited on the surface of the membrane initially. Okay. Then again the deposition layer increases, right, slowly the thickness increases. Okay. After certain time what will happen, this will become a cake. Okay. Under the pressure it will become cake, or we can say it gel. So, what is the meaning of this? So, when this gel layer or cake layer is getting built up, so it will do two things. First is that your flux will decrease very drastically. That is because it is providing a huge resistance to the flow, either this way or this way, does not matter, okay, gradient filtration or closed flow. So, flux versus time. And then second thing is that it will also result in fouling. So, fouling can be external fouling, it can be internal fouling. Internal fouling means the foulants getting trapped inside the pores of the membranes. So, by all these things the membrane lifetime is getting reduced, and selectivity or flux is a concentration dependent, concentration, polarization or fouling dependent thing, as it is very clear from this picture. So, selectivity or flux decreases with progression time, and upscaling factor is very linear. So, the major membrane separation processes are microfiltration, ultrafiltration, reverse osmosis, electrodialysis and dialysis. You can see in the first three, so what is MF, UF and RO, the driving force is pressure gradient. It is a the delta P we can say. As you come from microfiltration to ultrafiltration, the size decreases. The size of the solutes that it will separate basically decreases. So, 10 to 0.1 micron in microfiltration, 0.1 micron to 5 nanometer in ultrafiltration, and less than 5 nanometer in RO. Then we have electrodialysis, in which electric field gradient is the driving force, less than 5 nanometer, and dialysis, that is concentration gradient, less than 5 nanometer. So, membrane has the ability to transport one component more readily than others because of the differences in physical and chemical properties between the membrane and as well as the permeating components. So, let us again understand that it is not the properties of the solute alone that is deciding the permeation or separation, but the membrane properties also plays a big role. So, we can have different types of separation in membrane. So, we can have a liquid separation, we can have a liquid gas separation, we can have a gas separation. So, in the membrane processes, the driving force can be gradient in pressure, concentration, electric potential or temperature. Other than driving force, membrane itself plays a major role in determining the selectivity and flux. The membrane material basically. So, nature of the membrane determines the type of application, ranging from the separation of microscopic particles to the separation of molecules of an identical shape and or size. Let us understand the transport. So, transport through the membrane takes place as a result of driving force acting on the components in the feed. Permeation rate through the membrane is directly proportional to the driving force. So, the flux force relationship is this. So, J equals to minus A dx by dx. So, A is the phenomenological coefficient and dx by dx is the driving force expressed as the gradient of x. X can be capital X, X can be either temperature, it can be concentration, it can be pressure, okay, and along a coordinate x which is perpendicular to the transport barrier. Now, for a pure component permeating through a membrane, it is possible to employ linear relations to describe the transport. However, when two or more components permeate simultaneously, such relations cannot be generally employed since the coupling phenomena occur in the fluxation forces. If you can recall the lecture on transport in membrane, in which we have discussed non equilibrium this one thermodynamics, in which we have discussed about the L1, L2 and different coefficients like the main coefficients and coupling coefficients L11, L12, L22, L21. So, I hope you will recall those. So, in today's lecture it is not possible to describe everything. Let us see what are the different types of membrane that are available commercially. So, basically we can group into isotropic membranes, anisotropic, ceramic or inorganic membranes and liquid membranes. So, isotropic membranes are basically microporous membrane, they can be non-porous membrane also, electrically charged membrane. So, in isotropic microporous membrane you can see the membrane pore size are more or less homogeneously distributed, you can see in this, okay. And we have in a non-porous dense membrane which something looks like this, okay. So, this is also isotropic anisotropic, it is homogeneous nature. Very small pores usually may be present, but they are not visible or cannot be seen, right. And electrically charged membranes, that also comes under isotropic membranes. So, different types of cationic groups or anionic groups are fused along with the membrane material, so as to make it as either a cationic membrane or a anionic membrane, or we can have a bipolar membrane. So, where both cations and anions are present. Then let us go for a anisotropic membrane. So, the structure is like this. You can see the two distinct layers here. Okay, this is one layer and this is another layer. So, here the pore size is small, right, and here the pore size is bigger. So, this is actually providing, so basically you can see that two different porous membranes are fused together. So, the bottom portion, this one is providing the support, whereas the top portion this one is doing the separation. So, all the separation is achieved by the top layer. So, thickness of top layer plays a very big role. Then we have ceramic membranes. So, this is an example of tubular ceramic membranes. Ceramic membranes can be prepared by various materials, right. Then we have liquid membranes. We will be discussing in one class the liquid membrane concepts. So, you just can understand that liquid membrane is something in which the membrane itself is a liquid, right. Now, to enhance the membrane stability, liquid membrane material has been impregnated inside the solid porous membrane. So, this is a solid porous membrane, usually a microporous support, microfiltration support, in which the pores are getting filled with the liquid membrane, and then the separation will be done by the liquid membrane. The microporous membrane is only providing the mechanical support. So, if we talk about membrane processes classification, we have already discussed about this. So, we can classify membrane based on material, based on membrane structure and morphology, based on operational modes, based on charges and based on driving forces. So, let us now see that actually what is the basic difference between microfiltration, ultrafiltration, nanofiltration, reverse osmosis, or 4 distinct pressure driven membrane processes. So, you can see in microfiltration everything here is getting to the permeate side, including the viruses, whether it is bacterial and suspended solids will be retained. So, please remember, as we come down from microfiltration to ultrafiltration to nanofiltration to reverse osmosis, the size of the pores decreases. Okay. So, pore size is decreasing as we come down from microfiltration to ultrafiltration. That means what? Small and smaller molecules will start retaining. So, let us see ultrafiltration. You can see virus will also be retained here, but virus was not getting retained in the microfiltration because by the virtue of the size. When you come to nanofiltration, multivalent ions also get retained, few may pass through because of the sizes again, right, and reverse osmosis will retain everything, it will only allow the passage of the solvent or water. So, this slide just gives us an idea about the different applications that can be achieved using the 4 distinct pressure driven processes: microfiltration, ultrafiltration, nanofiltration and reverse osmosis. So, let us talk a little about the materials, okay, that is being used to prepare membranes. So, the first and foremost is of course polymers. Before that, in the porous membranes, actually porous membrane contains fixed pores in the range of 0.1 to 10 micron for microfiltration and 2 to 100 micron for ultrafiltration. Now, the selectivity is determined by the dimensions of the pores, but the choices of material affects the phenomenon such as adsorption, chemical stability under actual conditions. The main problem in microfiltration and ultrafiltration membrane is flux decline. Okay, this we have discussed many a times. Okay. So, therefore, again we will be discussing when we will discuss microfiltration and ultrafiltration in detail as a processes basically. So, therefore, the choice of membrane material for such process is based on prevention of fouling and cleaning procedure after it is fouled. You do anything, membrane will be fouled. So, you have to take care in such a way that if you choose a membrane material properly, that it is a less foulable material and easily cleanable, that is always better for a microfiltration and ultrafiltration system. So, frequently used polymers used in microfiltration membrane are polycarbonate, polyvinylidene fluoride, polytetrafluoroethylene, polypropylene, polyamide, polysulfone, polyetheramide, and I just forgot to mention PES is a variety of this polyether sulfone. Okay. So, for non-porous membranes are primarily used for gas separation and pervaporation. The choice of material is determined by the type of application, and the polymer type can range from elastomer to glassy material. These are the materials which are being used for making polymer membranes. Cellulose, we have cellulose acetate, which is being, cellulose is the most abundantly available material in earth, okay, from the plant sources basically. Then cellulose acetate is being developed from cellulose by triacetylation reaction. Okay. Then we have polyamides, we have polysulfons, and there are other materials, I have just skipped it. So, polymeric membranes have low mechanical stability and fouling problems. So, on the other hand, inorganic membrane possesses better properties such as high chemical, thermal and mechanical stabilities. So, inorganic membranes also suitable for harsh conditions such as corrosive environments and high temperature applications. Hence, compared to polymeric, inorganic membranes have more advantages. So, the inorganic materials that are being used for preparation of membranes are ceramic, carbon, silica, zeolite, various oxides, metals such as palladium, silver and their alloys. So, you can see this is a composite membrane basically. So, here you can see there are three distinct layers, one is this red one, another is this one, another is this one. So, the first one is the separation layer, that is doing the separation. I do not think that always a composite membrane or an isotopic membrane will have only 2 layers, it is not like that, mostly it can have 3 layers, it can have more than that also, but usually not more than 3 layers. So, in this particular case, in this application you can see the distinct layers, this is the first one, the separation is being done, this is the second layer and this is the microporous layer, third layer, the titanium support. So, the first one is separation layer, okay, which is used by the Sol-Gel methods. The second layer is a distinct ultrafiltration layer and the third one, this one which is providing the support, is the microfiltration layer, okay, and below that we have coarse layer, okay. So, then let us discuss about membrane module. So, the module is what? So, module is something that is actually holding the membrane, okay, it is the smallest unit into which the membrane area is packed. So, the module is the central part of the membrane installation and the simplest design is one in which a single module is used. There will be an inlet for the feed and outlet for the permeate and retentor for the most basic membrane module. The permeate stream, the fraction of the feed stream which passes through the membrane, the retentant stream is the fraction retained on the membrane. So, we have different types of module configurations, flat sheet and disc type, hollow fiber, tubular type. So, in flat we can have a flat and flame type of module. So, we can have a spiral wound module, okay. So, we can have a hollow fiber or tubular module. So, this is a hollow fiber system, we have capillary modules, we have tubular modules, okay. So, this also we have discussed in detail. So, I am just quickly going through little basics so that you can recall what we have discussed, okay. So, we have two basic system designs of the membrane. So, the first one is single pass system in which a feed is coming, we get a retentate and we get a permeate. So, this is single pass system and there is a recirculation system. So, feed is coming here, okay, we get permeate here, we get retentate here and part of retentate we can say addes, that is getting recycled and mixed with feed. So, this is being done for specific applications so as to maintain the feed concentration, okay. So, choice of module configuration as well as arrangement of the module in a system depends on several features, several characteristics features or parameters. So, the first one is of course the cost is most important thing. Second is type of separation problem. So, ease of cleaning, ease of maintenance and operation, ease of compactness of the system, scale and the possibility of the membrane replacement. We can have two different types of module operations. So, we can have a dead end operation, we can have a cross flow operation. This is the dead end operation. So, you can see this is your membrane on which of course this concentration polarization cake layer is getting deposited, your permeate is coming here, okay, you are applying pressure. So, your feed is fixed volume. So, whatever you have given, then you are pressurize the system. So, the feed volume is continuously decreasing and permeate is getting out here, okay. So, you get your permeate, so your feed and then be getting retented on this surface of the. So, what is happening, you see the flux profile, flux, there is a drastic fall of flux here, okay, because it is a dead end filtration system, right, and cake layer thickness increase is also, it is almost complementary to each other, the way the flux is decreasing, in the same way the cake layer thickness is increasing. Now, another one is the cross flow system, okay. So, here the feed is flowing across the membrane surface, permeate is coming here, you are pressurizing here and you are getting the concentrate or the retentate here. the flux profile is little better, or why little is far better than the dead end filtration. Okay. So, you can see there is no instantaneously decrease in the this one flood, it is more or less better profile, and the thickness are also complementary to each other. So, you can say that cross flow filtration is always better. However, dead end filtration are also used in lab scale to characterize membrane and to generate data. So, various types of flows can be distinguished inside the modules. So, co-current, counter current, cross flow and perfect mixing or completely mixed flow. So, in co-current and counter current operations, the feed and permeate stream flow co-currently, parallel plug flow or counter currently along the membrane. So, this is the first one is the co-current. So, feed and permeate, okay, feed and sweep is getting actually flowing in the same direction, right. So, in the second is counter current, in which feed and sweep is flowing in opposite direction. The third is called cross flow, the usual cross flow which we just discussed, and fourth is the perfect mixing. Here both the permeate side and the feed side are getting well mixed. So, the mixing enhances the rate of mass transfer, basically that is the idea to mix it, okay, but it is not done always in all the systems. So, now let us just quickly discuss the different preparation methods. So, first the preparation of synthetic membranes. So, we can have symmetric non-porous membranes, we can have symmetric porous membrane, we can have asymmetric porous membrane. So, we will just see one by one in a single slide. So, symmetric non-porous membrane, we have solution casting. So, if you recall we have discussed how to do that. So, you take a polymer sample, basically it is a solid, dissolve it in a solvent in which it is completely dissolvable. So, you got a solution which is called polymer solution, right. Then you cast it on a plate, something which is being shown here, okay. It can be a stainless steel, it can be a glass plate. Once you cast it, then there is some roller type of arrangement with a knife, then evaporation will take place, okay. The material will settle down, right, and then finally this can move here in this direction, in this direction, it will decide, the blade will decide the thickness of the membrane. So, it is a very crude way you prepare symmetric non-porous membrane, is called solution casting. Then we have melt extruded film. Here the same, once you cast the solution, that means the polymer solution, you are pouring here, okay, a conveyor belt system arrangement, okay. So, it is rotating in this direction, right, the stainless steel balls, and there is a conveyor belt here, basically it is stainless steel, right, and then you are pushing air here, okay. So, basically it is dry air, okay. So, dry air is helping in the evaporation of the this one solvent from the solution, okay. Then you take a dry film. So, this is anyway a good way to prepare actually symmetric non-porous membrane. In mostly commercial applications this type of technology is being adopted. Then symmetric porous membranes, we have other so many different types of processes. I have just tried to give you the schematics to understand something. So, the first one is, let us say, understand sintering. Sintering is a process in which we are taking powder materials, it can be any other materials also, and doing some thermal treatment at very high temperature. So, let us discuss about the powder materials. You see the first one is the loose powders, okay. So, initially you just pack it, so it becomes a little better packing, okay, initial stage. Then the temperature is being applied here, okay. Then it is the intermediate stage, and slowly the interspaces will disappear, this will disappear, and it will result in pores. So, these are basically the pores. So, it is the easy process, easy way to do. The second one is stretching. So, basically once you have once you are something is coming from the extruder, okay. So, after extrusion basically, so that goes to stretching, you are just stretching. Manual stretching also can be done, usually it was done when membranes were being prepared in labs. So, you can do the longitudinal stretching inside an oven also, so that evaporation also happens, okay. Or you can do the transverse stretching, then go for setting. So, then we can have track etching. So, in track etching, the polymer which is already been casted into a film will be subjected to various different intensity of radiation sources. So, the radiation will fall on the polymer and it will develop cracks. Now, the cracks will have the loose materials, those can be cleaned when it goes through a etching bath. In template leaching more or less the same process. So, you can just go back and again see what we have discussed during our template leaching discussion. So, then is the asymmetric porous membrane. So, you can have precipitation by solvent evaporation, we can have precipitation from the vapor phase, we can have precipitation by controlled evaporation, we can have thermal precipitation, we can have immersion precipitation. So, in all the cases all phase these are all phase separation processes. A liquid polymer solution is precipitated into two phases. The first is a solid which is a polymer rich phase, second is a liquid which is a polymer pore phase that forms the membrane pores. Then let us understand composite membranes. So, composite membranes are anisotropic membranes basically. So, we can have a 2 layers composite membrane, we can have a 3 layer composite membrane, we can have a 4 layer composite membrane. Okay. So, the first one, as we have already discussed, the selective layer, the material A, okay, which is doing the separation, the thickness should be as low as possible, so that resistance to flow will be less. Then we have another layer, basically maybe ultrafiltration range, then we have a microfiltration range layer, and we can have a coarse filtration range here, right. So, this is how actually this one composite membrane is prepared by interfacial polymerization. This is one of the most important development, okay, in the membrane science, the technology development of interfacial polymerization. So, one porous support membrane is there. So, I am impregnated this with some amines. So, this black whatever you are seeing, so this is amines. Okay. So, now the membrane is amine loaded. Now, this once it is done, so another non-aqueous medium I am bringing in contact with them, which is basically a diacid. Okay. So, diacid chlorides whatever it is, so it can be different. So, this amine and diacid will react with each other and it will do cross linking. Okay. So, this cross linking will result in the polymers. Okay. So, now you are seeing the some cross linking reaction happening here, then it will become a polymer structure and it will be so nicely attached to the pores of the membrane support, that it will not come out easily, because it is a reaction, by reaction it has been developed. Okay. So, this is how by interfacial polymerization you develop different types of composite membranes. So, you can have composite membranes by the usual deep coating method, which is extensively used in the lab scales. So, let us say you have a small circular shaped ceramic membrane and I want to develop a composite membrane. Okay, I want to put a very thin layer of polymeric support over it. Okay, so what I do, I dip it inside the polymeric solution or the coating bath. Okay, slowly and take out slowly. So, how you are dipping it and at what rate you are taking it, all these are parameters to be that affects the final features. Then you dry it and you get your composite membrane. It is a easy way to do it, right. So, otherwise you can have plasma polymerization. It is an excellent method. You are generating plasma to do polymerization basically. Okay. So, the gas is coming, it is getting ionized, plasma is getting this one generated, then those are getting deposited on the surface of the membrane, and in the vacuumized oven it is happening. However, the process is very costly. Though we have discussed, just I wanted to show you this slide to understand again or recall again how the composite membranes looks like basically. So, the first one is the critical separation layer, the selective layer, this one. Okay. So, pore size is usually 0.4 to 5 nanometer, thickness is single or multiple thin layers, materials are basically oxides, the uses in reverse osmosis, nanofiltration, molecular sieving. Then the primary layer, the pore size is almost 0.005 to 0.5 micron, 1 to 20 micron thickness in the UF range. Okay. C uses is ultrafiltration and microfiltration. Then we have porous supporter substrate. Okay, 0.5 to 50 micron, thickness is greater than 400 micron. Okay, depth filter and surface cake filter, even coarse filter also. So, now let us understand quickly the sol gel process, one of the most important breakthrough again, just like interfacial polymerization in ceramic membrane development. Okay, so we can have two different routes. So, we have a alkoxide precursor, we can have a colloidal gel route, we can have a polymeric gel route. So, both preparation routes make use of a precursor which may be hydrolyzed and polymerized. Two reactions are happening. I am not showing again the reactions here, you can just revisit and see the reactions. So, one is a hydrolysis reaction, the next is polymerization reactions. Now, these processes must be controlled to obtain the required structure, and alkoxide is frequently employed as a precursor, and the hydrolysis and polymerization condensation reactions happen, right. let us understand how actually transport happening in porous and non-porous membrane. In non-porous membrane, which is dense membrane, the separation is happening through solution diffusion. Okay. So, the solutes are coming and they are getting deposited on the surface of the membrane. Slowly they will get themselves dissolved or solubilized inside membrane material, then they will diffuse, again molecular diffusion of course, then they will permeate. So, this is what is called solution diffusion. Solubility, diffusivity both are important. Porous membrane, so many different types of things. So, if the pores are, if the solute is bigger than the pore size, okay, then the separation will be high because most of them will be retained on the surface. Okay, that is called molecular sieving mechanism. Okay, and if your lambda by r is lesser, or let us say the mean free path is higher than the pore diameter or pore mouth, okay, then you will have Knudsen diffusion. This is more prevalent for gas separation. Okay. Now, then the next thing that we have discussed in subsequent few lectures, 1 or 2 or 3 I think. So, is the characterization different types of membranes, porous membranes and non-porous membrane. Then we have discussed also the characterization of your ionic membranes, right. So, one important but often not clearly defined variable in the characterization of porous membrane is the shape of the pore or its geometry. It also plays a very big role. In order to relate pore radius to the physical equations, several assumptions have to be made. Two equations which we have already discussed many a times. First one is your Hagen-Poiseuille equation or Poiseuille equation. The second is the Kozny-Karman equation. Now, what is the difference between these two equations is just the assumptions. So, in Poiseuille equation the pores are considered or assumed to be parallel cylinders, which is not true in of course real life, and in Kozny-Karman equation the pores are considered to be the voids between the closely packed spheres. So, you can see something like this. So, this is what is the pores, okay, and here in the case of parallel cylinders it is just like this, okay. Right. So, only zeolites have such distinct features, parallel, otherwise you do not get in any other commercial membranes. So, we need to understand the nominal and absolute rating which we have discussed during the characterization. So, the membrane can be characterized by a nominal or absolute pore size. So, with an absolute rating which is this, okay. So, every particular molecule of that size larger is getting retained on the surface of the membrane compared to what? Compared to the pore size. So, the absolute rating should not be confused with the largest particle passed by a filter under operating conditions. Okay. So, it simply determines the size of the largest particle which will pass through the filter under very low pressure differentials and non-pulsating conditions. On the other hand, a nominal rating indicates the percentage of 95 to 98% of the particles that is getting retained, okay, on the surface of the membrane. So, when you talk about the characterization of porous membrane, so we characterize two different things. First is structural related parameters which are pore size distribution, top layer thickness and surface porosity, and then permeation related parameters. So, determination of the actual separation parameters using solutes that are more or less retained by the membrane, which is called cutoff membrane or cutoff measurement, or we can call it molecular weight cutoff experiments also. It is often very difficult to relate structure related parameters directly to the permeation related parameters because of the pore sizes and shape are not very well defined. So, the first one is for the porous membrane characterization microfiltration basically is the bubble point method. Here what is being done is this. So, you take the membrane, put it in some module or some arrangement something like this, okay, then wet the membrane, right. So, the top portion of the membrane is getting wetted, the pores are also getting filled. Okay. So, with the liquid you can see the pores are getting filled here, right. Then you pass nitrogen or some inert gas from the bottom. So, the air or nitrogen will push them itself through the bottom of the membrane, and the very nice thing about this particular simple method is that only the pores which are active will be characterized, because the dead end pores which are blocked, let us say the pore is blocked like this, another pore is open. So, these are this is a pore, this is a pore. So, only the active pore will be characterized, this dead end pores will not be characterized. You use the Laplace equation Rp is equal to 2 gamma delta p cos theta to find out the pore radius. So, this is the surface tension, Rp is the radius, okay, and theta is the angle. So, a little modification of this method is bubble point with gas permeation, in which actually first initially you measure the flux using the dry membrane, then wet the membrane, and again see how the this one gas is basically getting diffused inside the pores of the membrane and displacing the liquid. So, another one is the mercury intrusion method. This gives excellent accurate measurement because mercury do not wet the membrane. Okay. So, you can use this again the same Laplace equation by substituting the theta and this interfacial surface tension values. We can reduce this equation getting reduced to 7492 divided by delta p, which says what? Rp is a direct consequence of delta p. Okay. So, the volume of mercury can be determined very accurately. So, the pore volume determination can be done very accurately. Pore size distribution can be also done accurately. So, at lowest pressure the largest pore will be initially filled. Okay. Then you increase the pressure, the smallest pore also will fill. The cost is very high of this particular apparatus. So, the next is permeability method, which are actual real experiment. If you assume capillary pores to be present, the pore size can be obtained by measuring the flux through the membrane at a constant pressure using the Hagen-Poiseuille equation. So, here J is the water flux through the membrane at a driving force delta P by delta x, delta P being the difference in pressure Newton per meter square, delta x is the membrane thickness. So, tau is the tortuosity factor, epsilon is the surface porosity, then we have this R is pore radius, and this is eta is viscosity. So, pore size distribution can be obtained by varying the pressure. It is not essential that the liquid should wet the membrane. Then if you talk about the characterization of ultrafiltration membrane, the most important experimental method or analytical method is the gas absorption and desorption. You are adsorbing a particular gas on the surface of the membrane and then again desorbing it. So, you will see this is a hysteresis loop. We have discussed in detail what is hysteresis, what are the different types of hysteresis, why hysteresis happens. So, please go back and just revise and recall what we have discussed. Okay. And we can have a thermopyrometry. So, what you need is a DSC instrument, differential scanning calorimetry system, which is again a costly instrument, and the calorific measurement of this solvent or liquid is being carried out in this particular one. So, the extent of cooling or undercooling is being measured. Okay. In thermopyrometry method, this is also a very good method, but you need a DSC for that. So, we can have perm pyrometry. So, in perm pyrometry we will have a condensable gas and a non-condensable gas. So, nitrogen, oxygen are non-condensable, ethanol is condensable. So, okay. So, the diffusivity of oxygen this side and the diffusivity of nitrogen this side in the presence of ethanol is being measured. So, that will give us the pore size, pore diameter, everything. So, a liquid displacement is another method. In just like bubble point method, here gas is not being used to displace the liquid. Here another liquid which is immersible with the already present liquid, okay, is being used to displace the liquid. Okay. So, you see this is a displacing liquid which is of course immiscible with the stagnant liquid. Okay. This is also a very good method. You should ensure that both the liquids, okay, they should not be miscible at all. Then let us quickly discuss about the transport in membrane. So, two types of transport happens, passive and active transport. Passive transport is a direct consequences of the differences in concentration or other forces. Okay. So, that means it is happening from higher concentration to lower concentration, whereas active transport happens from lower concentration to higher concentration against the gradient of its concentration, okay, or any other thing. So, to do that you can understand that you need some sort of energy. So, we need some extra energy, okay, to carry out this. So, you can have facilitator transport where there is a carrier present, right. So, the carrier will bind to the solute and help to diffuse the solute that is being transported through the membrane, okay, and it will take it to the permeate side, then it will again dissociate itself. Right. So, the driving force is delta x by L, delta x is the gradient and L is of course the thickness of the membrane. So, we can have either potential, chemical potential as a gradient, or we can have a electrical potential as a gradient. So, these active transports are mostly they are biological systems, we will see in biological systems. Okay. So, glucose transport. So, transport of glucose, okay, glucose from blood to liver cells, okay, because in liver cells the glucose is present in very high concentration. So, we are trying to act against the concentration gradient, that means from low to high we are going, okay, not from high to low. So, we need some energy. So, energies are being provided in biological system by ATPs, adenosine triphosphates, or ADP or NADP, and there are so many other varieties also. The most important property of the membrane is their ability to control the rate of permeation of different species. Permeation mechanism can be explained by two things. First is the transport through porous membrane. So, separation occurs through pores, then transport through non-porous membrane, dense membranes. So, here permeate dissolve in the membrane material, then diffuse through the membrane down a concentration gradient. So, solution diffusion model is being used here. Okay. So, transport of gases through porous membrane. When a asymmetric membrane or composite membrane is used in gas separation, the gas molecules will tend to diffuse from the high pressure to the low pressure side. Now, various transport mechanism can be distinguished. So, you can have a Knudsen flow in narrow pores, we can have viscous flow in wide pores, we can have surface diffusion along pore walls. Okay, so, you can see this is a composite membrane, 3-layer composite membrane. The top layer bulk diffusion is happening, the narrow pores we have Knudsen diffusion, the mean free path is but more than the pore diameter, and then we have wide pore where is viscous flow is happening. And transport in non-porous membrane. So, when the sizes of the molecules are in the same order of magnitude as with oxygen and nitrogen or hexane and heptane, porous membrane cannot affect a separation. So, in this case non-porous membrane must be used. However, the term non-porous is rather ambiguous because pores are present on a molecular level in order to allow transport even in such membranes. The existence of these dynamic molecular pores can be adequately described in terms of free volume. Initially, transport through these dense membranes will be considered via somewhat simple approach. Thus, although there are some similarity between gaseous and liquid transport, there are also a number of differences. So, in general the affinity of liquid and polymers is much greater than that of between gases and polymers, that is the solubility of liquid in a polymer is much more higher than that of a gas. So, sometimes the solubility can be so high that cross linking is necessary to prevent polymer dissolution. In addition, a high solubility also has a tremendous influence on the diffusivity, making the polymer chains more flexible and resulting in an increased permeability. So, basically the transport of gas, vapor or liquid through a dense non-porous membrane can be described in terms of solution diffusion. So, permeability equals to solubility into diffusivity. So, solubility is a thermodynamic parameter and gives measure of the amount of the penetrant served by the membrane under equilibrium conditions, whereas in contrast diffusivity is a kinetic parameter which indicates how fast a penetrant is transported through the membrane. Diffusivity is dependent on the geometry of the penetrant, for as the molecular size increases the diffusion coefficient decreases. However, the diffusion coefficient is a concentration dependent term, okay, and even large molecules, organic molecules basically having the ability to swell the polymer can have large diffusion coefficients. So, in a nutshell we have discussed the concepts and the fundamentals of the membranes and various aspects of membrane materials, the modules, how to prepare membranes, transport across membranes, and how you will prepare ceramic membranes. So, I hope you have enjoyed this particular lecture. So, then next class onwards actually we have already started osmosis, the concept of osmosis which I have not covered today, just last class we have discussed. From the next class onwards we are starting reverse osmosis. Okay. So, the membrane processes, then we will discuss microfiltration, we will discuss ultrafiltration, nanofiltration, pervaporation, okay, various hybrid systems and so on. We will go on, there are other things to discuss also. So, you can refer these textbooks, mostly it is taken from Mulder, okay, and of course from Professor Becker's book as well as Professor Nath's book. Okay. So, thank you very much, and in the next class we will discuss about the RO and the pressure requirements, high pressure, low pressure RO, membrane materials and modules of RO and the transport in the RO. So, in case you have any questions, query, do feel free to write to me at kmohanty, okay, at iitg.ac.in. So, this my webmail ID is already there in most of the lectures, or you can free to ask your questions or queries in the forum also. So, thank you very much.